at is 0. Now, notice that if this first condition is false, in other words, it is null, then this second condition here is meaningless, and in fact, it would be a bug to try to execute it. Right? So, of course, given the way that this is defined, it should not try to execute it. Right? It should the compiler should say, okay, well that's not going to happen, and so I don't need to try that. So with this one, again, you've got true. You test true, true, and then false. But that if you test that with false, then this can't be any value one way or the other, right? Because it's nonsensical to ask what a null pointer is pointing at. So in order to get condition coverage, you'd actually have to test true and false, right? And then true, and then false, and don't care. So that would actually, in that case, multi-condition decision coverage and condition coverage would be the same thing, and multi-condition coverage would result in a meaningless test. You couldn't actually achieve it because we couldn't have false and true, or false and false for that matter, because again, this condition is undefined in the case that the pointer is null. And lastly, here, let me clear this out. We look at 13 through 17, right? And now, so this is an OR. So you notice that this is the logical backward or logical opposite situation of the lines 1 through 5. So if the A less than or equal to 0 clause evaluates to true, then we don't have to go on to evaluate this because the overall compound condition will evaluate to true. So condition coverage would be the same thing. It'd be true, false, and true, false. Now, in order to check that, remember that in order to actually get this to evaluate in a compiler, you'd have to make sure that the execution flowed there, right? So this would have to be false in order for this check to happen, which is the opposite of what would happen here. This would have to be true for this check to happen. So we would have to get, we have to say false, true, and then true, false in order to get condition coverage. Now, for multi-condition coverage again will be the same as before. It's the true, 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 false, false, true, false, false. In this case, we can actually do that, which was not true up here because of this condition here. And in the case of multi-condition decision coverage, it's true and don't care, and then false, true, and false, false, the things that we need to look at there. So as you can see, that can get a little bit hairy, and just explaining it can be a little bit challenging, and then so you can imagine trying to figure it out, tracing through a program. So it's good to have tools to do this, but you do need to understand that, as I said, things like multi-condition coverage in some cases can be impossible, like in the situation in lines 7 through 11 on this slide. Okay, now, McCabe cyclomatic complexity. This is something that you might run into if you are looking around at tools. There are tools to support this. And basically what Tom McCabe was trying to do, and I saw that somebody sent the paper, and I'll mention the link when we go through the Q&A. You'll see this if you read his paper. Basically what McCabe was trying to do in his research on this was to figure out why it's so hard to write programs without bugs in them. And what he stumbled on was this realization that you can look at the amount of branching in the program as a surrogate metric for its complexity. Now, by surrogate metric, what I mean is the thing that you can measure directly, which tells you a lot about something that is very difficult or perhaps impossible to measure. Now, there are many different ways that we could try to measure the complexity of the program, and some of them get pretty tough to measure. Like, for example, Halstead's complexity measure, which you can find discussed in Beiser's book, Software Test Techniques. And that's a real challenge to try to get your head around what that means. McCabe said, well, let's make this simple, that programs are complex because there's branching, where there are situations where one of two things is going to happen, or one of n things is going to happen in the case of a switch case. And since that's the situation, as you write the program, you have to keep straight in your head the possibility that there are multiple things that can happen. And that information is something that has to get stored. And there's psychologically, there's some work that's been done on this, and it's not just psychological; it's actually brain science. There's a part of your brain that holds the working memory, the short-term working memory, and it is very limited in its capacity. It can hold about 10 things at once at most, and then it starts to get pretty unreliable. So what that means is that if we look at the amount of branching, and if it goes well above 10, or even according to McCabe, even above 7, then the likelihood of making a mistake goes way up. And so what this does is it looks at this metric, it looks at the amount of branching in the code, and then it says, look, if the complexity number is very high, then we would expect a higher than normal number of bugs in this particular part of the program. And for those of you who have heard of this principle before, that's the testing principle of bug clustering, or defect clustering. So defect clusters are going to tend to be associated with highly complex modules, according to McCabe's theory. Now, there is some counter literature on that. Some folks from IBM did a study on that about 4 years ago, I think it was, 4 or 5 years ago. This came out in Software Quality Professional, and you might want to look that up if you're really interested in this metric for both research done pro and con on it. But basically, that's his assertion, that programs would tend to be more buggy if they're high complexity, and that certainly does make sense. Now, also, that they're harder to work on, so they're going to tend to be regression prone. So, and that also does make a lot of sense too. If you ever looked at what's sometimes referred to as spaghetti code, it's going to have very high complexity and it's very difficult to work on. Now, there's also this concept of basis paths and basis tests, and the complexity number is the same as the number of basis paths, and which is the same as the number of basis tests required to cover the control flow graph that's created when you do this analysis, at least according to the theory. Now, this gets pretty hairy here. This is fairly complex stuff. So I'm going to show you the theoretical technique that McCabe defined for how to calculate cyclomatic complexity, and then I'm going to tell you a couple shortcuts to that. So we take that Fibonacci program that we've been looking at so far, and we create a control graph of it. It would look as shown here. Now, in the control graph, what you've got is you've got an entry block and an exit block. And that's what you start with. You have this bubble or circle. It's called a node here. You start with an entry and an exit point, and then for every sequence of 0 or more executable statements, for example here, you draw a arrow referred to as an edge. And anytime you get to a decision point, a branch, you draw another node, this guy right here, you see, and then out of that node comes the number of decisions that can be made. Now, in the case of an if statement, there are 2. In the switch case, there are as many as case blocks plus the default. So we have an edge now going out of here. This is the yes, n is less than 0. So that corresponds to this chunk of code right here. And if no, then we do the else block. So now we have this printf and these pp and stuff going here, and then that's this edge here. And then now we have the loop, that guy there, I less than n. And as long as that's true, we're going to loop around here, right? So that's the body of the loop, corresponds to this thing here. And then we have this